Okay, with that, we begin our second set of Spotlight Talks. Our first speaker in this set is going to be Kevin Ellis, and he'll tell us about learning libraries of subroutines for neurally guided Bayesian program induction.
Hi, thanks. So what we want to do is we want to make machines that learn how to program. And we want to do this without giving it example programs, and we also want to do it without giving it a powerful domain-specific language to start with. So we have a new algorithm called Explore, Compress, Compile, or EC squared, for accomplishing this task. And the way it works is by jointly acquiring two different kinds of programming expertise. The first thing that it learns is a library of functions that are tuned to a domain of problems. And the second thing that it learns is how to use those functions in order to quickly solve new problems in the future. We apply it to several different problem domains, and on the slide you can see example programming tasks from 3 domains. So for list processing, we're learning how to reverse a list. For text editing, we're taking some names and putting doctor in front of the last name. And for symbolic regression, we're looking at a curve and then writing down a function that describes that curve. So imagine that you had to solve the following programming problem from these input outputs. It's probably pretty hard to tell what's going on. But now imagine that I told you that you're starting with a library which has the following procedure. So you don't have to know what that Lisp code is doing like specifically, but you can think of it as like taking a list and a predicate and then getting all the elements out of the list or filtering the list whenever that predicate returns true. So if you have this in your library, then you could write the following piece of code, which just says take the input list and then filter all the elements that are bigger than 2. So if you take this EC squared algorithm and run it on a corpus of around 200 list processing problems, what it discovers are a bunch of sort of standard list manipulation routines, things like how to append lists or how to take the maximum element of a list. So you can think of EC squared as a hierarchical Bayesian model where at the top there's some latent library or DSL which generates programs which then solve programming tasks, which is what we actually observe. And we're also going to infer a neural network called a recognition model, which is going to predict a distribution over programs that are likely to solve each task. We have a 3-step inference procedure for this model. In the explore phase, we search for programs that solve tasks, and the way that that works is we take our task and we pass it to the recognition model, and that biases a search over programs written in the DSL, and we search for the ones that solve the task. Once we have programs solving tasks, we update our DSL in the compress step, and the way that that works is we analyze the syntax trees of programs found during exploration, and we pull out fragments and add them to our DSL. During the compile phase, we train a neural network to help search for programs. And the way that that works is we sample programs from our DSL, run them to see what they do, and then tell the neural network, when you see this task that you just sampled, predict the program that you also sampled. And the advantage of this is that you can draw as many samples as you want, training on a very large corpus of problems. And then we just repeat these 3 steps, explore, compress, compile, in a cycle. So I've shown you some of the list processing problems that we applied it to. Here are some text editing problems where you need to manipulate some strings. And we start the system out with things like map and fold, and then it has to learn a library of routines which allow it to edit text. So here are 2 text editing problems. And the way that it solves this is by learning routines for doing things like appending strings, and then it sort of builds on itself in later iterations. So it learns how to append strings, and then later it learns a routine for putting a string in parentheses, which uses append. So in order to learn programs with continuous parameters, what we can do is we can differentiate through the program and set those parameters using gradient descent. So we tested this out on some symbolic regression problems where you have to write some code that fits points on a curve, and we added the twist that the recognition model gets to eyeball a graph of the function so it can get a sense of what kind of code it needs to write before it starts writing it. Very recently, we've been looking at generative graphics programs where the agent sees a picture and has to write some code that draws that image. So here are 90 pictures that we trained the system on. One way of examining the learned DSL is to draw sample programs and see what kind of images they produce. So prior to learning, they're mostly like lines and simple curves, and afterwards there's a lot of rich geometric structure. We can also take individual DSL primitives that were learned and put into the library and run them with different parameters. And when you do that, what you see is that it's learned interpretable geometric drawing routines for things like circles and lines and polygons. So we think that this combination of learning a library of functions as well as learning a neural recognition model for searching for code is a way of making program synthesis more generally useful for AI. For more information, go onto our poster. It's poster 24.